Alright, in this video we go over section 4.1, which is higher order derivatives, and we were going to use this to find the intervals where a function is concave up, concave down, and then use second derivative test to determine two things. Number one, to determine if we have points of inflection, and to determine if we have maximum and minimum points. Alright, so first let's define higher order derivative. So of course, when we have a function, we can find the first derivative, then find the second derivative using the same rules, and then the third derivative, the fourth derivative, etc. However, we're just going to do the second derivative because that's all we need, at least for this process of finding concavity and, um, and maximums and minimums and points of inflection. So the notation for the second derivative, well, we use the y prime notation. Now we use the y double prime, f double prime, f with a subscript with a 2 in the parentheses that denotes the second derivatives. For the other derivative symbol where we use the dy dx, well, we use d squared y with respect dx squared, that denotes the second derivative, and we have other operators that we have that are not very common. Actually, this one right here, the one I'm highlighting in green, we're going to use that later at the end of the semester when we take partial derivatives. All right, so let's find the first and the second derivative for each function. Well, for this polynomial function f prime of x, using the first derivative, well, that's a 3x squared minus 12, and that's the first derivative. And then we take the second derivative simply by taking the derivative of the first derivative. So the derivative of 3x squared, that's going to be 6x, and the derivative of negative 12, that's 0. Let's do a couple more examples. So for letter B, we have y equals the square root of x squared plus 1. Well, before we differentiate this one, let's write this in rational expression, or in rational exponent instead of a radical. So let's take the derivative of this. Let's use the other notation, dy dx, which equals 1/2 times x squared plus 1 to the negative 1/2. So what we're doing here is using the chain rule, and then we need to multiply by the derivative of the inside of the parentheses, which in this case is 2x. Notice over here how the 2's cancel. And well, I'm going to do two things at the same time. I'm going to write this this x squared plus 1 to the negative 1/2 power as x squared plus 1 to the 1/2 power in the denominator, that is with positive exponent. And in the numerator, we're left with this x right here. They're going to go right over here. Finally, let's just, well, for the first derivative, let's just rewrite this as x squared plus 1 under the radical, and this is final answer. To find the second derivative, dy dx, well, in this case, the second derivative, let me make sure this looks like a 2. So we do the following. Actually, I'm going to use this version right here. So I'm going to change the colors of this a little bit, do some color coding, and I'm going to change also, I'm going to change the color of this x. I'm going to do this orange. Alright, so to find the second derivative, recall, and in this case we're going to use the quotient rule. So recall that the quotient rule, the derivative of a quotient of f over g is f prime g minus g prime f, the whole thing divided by g squared. That is the derivative of the numerator times the denominator without differentiating minus the derivative of the denominator times the numerator without differentiating, the whole thing divided by the denominator square. Alright, so let's go ahead and do that. So let's take the derivative of the numerator. So in the numerator we have in orange an x, the derivative will be a 1 times the denominator without differentiating. Minus the derivative of the denominator, which in this case is 1/2 x squared plus 1 to the negative 1/2 times the derivative of the inside of the parentheses, which is 2x. Okay, and then the whole thing right here divided by the denominator squared, which in this case, oh, by the way, I forgot to multiply by the f, which is x, all right, which is this f right here. So the whole thing gets divided by the denominator squared, which is x squared plus 1 to the 1/2 quantity squared. And well, what's going to happen here? So number 1, a lot of the terms are going to get canceled. So on the one hand, see what's going to happen. So number 1, these twos cancel. These two x's are going to get multiplied, and I'm going to write this x squared plus 1 to the negative 1/2 in the denominator of only this term in the following way. That is, I'm going to do, well, 1 times the first term, that's going to be the square root of x squared plus 1 minus x squared divided by x squared plus 1 to the 1/2. The whole thing divided by another cancellation here. Notice how the 1/2 cancels the square, and that's going to leave us with simply x squared plus 1. Alright, so on the next step, let me keep writing d squared y over dx squared. That equals to the following. So the square root of x squared plus 1 minus x squared over the square root of x squared plus 1, the whole thing divided by x squared plus 1. So let's clean up this complex rational expression. Well, so in this case, we're going to multiply numerator and denominator by the least common denominator. So in this case, well, let's think of this radical x squared over 1 as over 1, and let's think of this quantity also over 1. So the least common denominator would be the denominator of all the common denominator of every of the denominators among all the simpler fractions that we have over here. So in this case, that LCD will be the quantity simply square root of x squared plus 1. Alright, so let's distribute this for the numerator and the denominator. So when I do for the numerator, we would end up multiplying radical times itself. Let's see what happens when we multiply a quantity by itself. This is equals to the square root of x squared plus 1 quantity squared minus, when we distribute this over here, we get the square root of x squared plus 1 times x squared. Notice that x squared is outside of the radical, divided by x square root of x squared plus 1. And then the whole thing divided by, well, what happens in the denominator. So we're going to multiply this radical over here. But in this case, just multiply across and leave it indicated the way it is. So simply the square root of x squared plus 1 times x squared plus 1. I'm going to continue on the next page, and before continuing on the next page, see how this x, the square root of x squared plus 1 cancels with this x squared, square root of x squared plus 1. Also notice how this square cancels that radical, and this squared y with respect to x squared, that will be, well, that's going to leave us with x squared plus 1 over here and x squared over there. All right, so let's see what we get. So over here we get the following. We get x squared plus 1 minus x squared and the whole thing divided by the square root of x squared plus 1 times x squared plus 1. And notice again how these two terms cancel. And we are left with, well, actually they don't cancel, do they? Did I mess up a sign? No, I think we're doing fine. Yeah. So that those cancel, and we end up with -1 square root of x squared plus 1 times x squared plus 1, and this is final answer. And yes, I was looking on my notes, and it looks, I thought I did a mistake, but I did a mistake on my notes, not here. All right, so for the next example, we have another quotient, another function which is defined by a quotient. Again, we're going to use the same rule. The derivative with respect x of a quotient f over g, that's f prime g minus g prime f, the whole thing divided by the denominator squared. So in this case, let's differentiate. Let's use the y prime notation. That's the derivative of the numerator, which is 2x, times the denominator, minus the derivative of the denominator, which is 2x again, times the numerator, the whole thing being divided by x squared minus 9, quantity squared. So simplifying this, that's going to give us, well, using the distributive property, and multiply. So that's a 2x cubed minus 18x minus 2x cubed. The whole thing being divided by x squared minus 9, quantity squared. All right, so notice how these two terms cancel, and leaving us with negative 18x over x squared minus 9, quantity squared. And that's final answer for the first derivative. However, we want the second derivative, so we are going to make use of the quotient rule a second time. And to get that done, okay, so number one, notice that negative in front of the derivative. I'm going to skip it for a while. Well, not really skip it, but rather, okay, so to take the second derivative, I'm going to write this negative outside and brackets. So that's going to be negative whatever I get from taking the second derivative. Because if I use this negative inside of the formula, which involves finding negatives, we are in risk of doing silly mistakes with too many signs, and I don't want to do that. So that's only my advice. I mean, if you want to use the negative sign, included in the process, that's fine. But my advice is to factor it out. And well, so we differentiate the numerator, which is 18x. I mean, the derivative of 18x is 18 times the denominator minus the derivative of the denominator, which this one right here will require a mini chain rule. So let me highlight. Oh, highlight. Okay, so that's the derivative of the numerator and times the denominator, just so you can see by color coding. Now, I'm going to take the derivative of the denominator, which will involve a mini chain rule, 2x squared minus 9, and to subtract 1, we get 1, which is an invisible one that we don't need to write. However, we still need to do a mini chain rule, which means multiply by 2x. And that's only the derivative of the denominator times the numerator itself, which is 18x. Okay? The whole thing being divided by x squared minus 9 squared, quantity squared. So we squared this a second time. Okay, so now we need to simplify this expression right here. All right, so rather than squaring this binomial to have like multiple terms, or distributing this quantity right there, which is what you may be thinking, but by first multiplying this, well, that looks like a lot of terms to deal with. We're going to take a different strategy here to simplify this. Instead, we are going to factor out GCFs in the numerator. You'll see how it's going to look instead. So y double prime equals negative. So notice how we have an 18 as a common factor. I'm going to factor out the 18. And at the same time, notice how we have 2 powers of x squared and 1 power of x squared. I'm going to factor one of the powers of x squared, not x squared only, but x squared minus 9. And I'm going to be left with the following. That's going to be left with x squared minus 9. That's the remaining power, minus 2 times 2x, which is 4x times x, which is 4x. So minus 4x, and then the whole thing divided by x squared minus 9, which is squared and then times squared. In this case, we have the power of another power. When we have power of another power, recall by laws of exponents, a to the m, which is raised to the n power, that's a to the m. And in other words, we multiply these two powers, and 2 times 2 equals to 4. Also, okay, what can we do here? Number one, it would be okay to just erase these parentheses here. We don't need them. And just write this in descending order of powers. Also, notice there is an invisible one here. And over here, let's see. I'm going to highlight this with green. Highlight this with green. Because see what's going to happen. In this case, because these are common factors, we can cancel this 1 power of x squared minus 9 with 1 over here to end up with 3. Also, y prime, that's going to be 18 times x squared minus 4x minus 9 divided by x. Actually, this is supposed to be x squared, and that's x squared minus 9 to the 3rd power. And here we have a couple of like terms that we can combine. So 1x squared minus 4x squared, well, that's going to leave us with 18. Don't forget the negative in the front. Negative. And that's going to be negative 3x squared minus 9 over x squared minus 9 quantity squared. Now, notice in the inside of the parentheses in the numerators, in the numerator we can further simplify by factoring the greatest common factor. We have a negative 3 and we have a negative 9. Both numbers share a negative 3, which is what we're going to do. We're going to factor that negative 3. So negative 18 times negative 3 that we get out of the parentheses. That's going to leave us with x squared plus 9, or not 9, actually plus 3. The whole thing divided by x squared minus 9, quantity squared. And notice here, we're going to have a multiplication of negative signs. In particular, this negative with that negative will turn everything into a positive. And all we need to do is multiply 18 times 3 to leave it with a 54 x squared plus 3, x squared minus 9, and that's our final answer. Okay. And well, this is the end of the first part of this video. For the second part of the section of this video, I'm gonna keep everything into a single video this time. So we are gonna use the second derivative to find the interval where a function is concave up or concave down. Recall in the previous chapter we used the first derivative of a function to find the intervals where a function is increasing or decreasing, and based on that we determine whether we have a maximum or a minimum in the function, or maybe no extrema. So that's what we did. So in this case, this is what we're gonna have. So when we have a function f and its first two derivatives that both exist on the interval a and b, for when we have the second derivative to be positive, the original function is concave up. On the other hand, if the second derivative is negative, then the original function f of x is concave down. And well, to illustrate this, let's look at an example with only a graph in which we will identify the intervals in which f of x is concave up or concave down. So concave down. And we are going to list the intervals in which it's concave down. Okay, so notice in this case we have letters A, B, C, D, and E. Just like I did in the previous chapter, I'm going to put numbers: -2, -1, 3, 4, and 5. All right, so concave down. What do we mean by concave down and concave up? So to relate this concave up and concave down. So okay, let me write this down. Concave. For concave up, you might think of the following. Think of shorthand writing the word, the expression concave up, which is concave up. This reads like the word cup. And well, if you think of a cup it's concave up, like in this case. So like over here it's concave up, over here it's also concave up, over here it's also concave up, you know, but otherwise the function is concave down. It's like an upside down cup, if you will, like this. So we are going to describe the functions in the intervals in which f of x is concave down. Okay, concave down, okay, let's draw all the intervals in which it's concave down. I can think of this interval right here. Also, I can think of this interval right there and this interval right there. Let's describe this using interval notation. Well, it's concave down from -infinity to -2. We are going to separate these intervals by commas, and then the next interval will be the interval 3 to 4 and 5 to infinity. Okay, now let's describe this time the intervals in which the function is concave up. That is, Here it looks like it's concave up. Here it also looks like it's concave up. And here it looks like it's concave up. Okay, so let's write. I know when we describe this interval, okay, it looks like it says concave or something like that. It's concave. So in this case, well, the first interval would be -2 to -1, comma -1 to 3, and 4 to 5. Those are the intervals in which the function is concave up. So the question here is, can we just put these two intervals together into a single one, and instead of that say -2 to 3? No, unfortunately this is incorrect. And that's because if we do that, we would be including this point right here. But notice at this point, it's neither concave up nor concave up. It's just a cusp in this case. It's just a sharp corner. So in this case, we need to write these two into two separate intervals. All right, so we're going to use the second derivative test and find points of inflection. Again, when for the first derivative test, we use this first derivative test to find the intervals in which the function f of x is increasing or decreasing. And from there, we determine whether we have a maximum or a minimum. In this section, we are going to find the second derivative, find the critical values, but well, we're not going to call them critical values, because if we use the critical values, we may be thinking of the values from the first derivative. So we're going to call them in a different way. We're going to call them hypercritical values. And this is just to make a distinction between the values that come from the second derivatives and those that come from the first derivative. All right, so in this case, well, what are we going to find when we do the second derivative test? Notice this point right here that I am circling, like this point, that point, that point, and that point. Those 4 points that I just highlighted are called points of inflection or inflection points, and those are the points in which the concavity changes. That changes from concave down to concave up over here, and at this point the function goes from concave up to concave down, and then from concave up to concave down again. So based on the change in the concavity, we are going to have points of inflection, just the same way, in a very similar way than in the first derivative test. If we saw a change between increasing to decreasing, we have a maximum, or if we had a change between decreasing and then increasing, we had a minimum. So over here, we're going to use that test to find the points of inflection, if any. And well, we're not going to do too many examples. I would like to keep this video short. Essentially, is a process in a very similar way than the ones that we did in the previous chapter. So all we're going to do is to add what the second derivative test is. So let's do one example. So let's determine the intervals on which f is concave up and the intervals on which it is concave down. Locate any points of inflection. Okay, so we need to find not the critical values, but the hypercritical values. And to do this, we are going to find not only the first derivative, but also the second derivative. 3x squared minus 2 times 3/2 of x, and the derivative of 5 is 0. Notice how these 2's cancel, and f prime equals to 3x squared minus 3x. Okay, so now that we have the first derivative, let's find the second derivative. That's 6x minus 3. And well, in this case, we need the hypercritical values, that is, set the second derivative equals to 0 to find that hypercritical values, and that's going to give us the values for which we will potentially have points of inflection. And we were going to look at the concavity of the function, and then x equals 3 over 6, which reduces to 1/2. So that's our only hypercritical value. And just the same way we did it in the previous section, we're going to draw a number line, plot the hypercritical values 1/2, and describe each interval. So this will give us two intervals to test. Number one, on this interval and that interval. So two intervals to test. The first interval will be described by -infinity to -1/2. And then that's the integral in purple, the interval in purple. The interval in green, that's -1/2, comma, infinity. Okay, let's erase these highlights here. Okay, so let's find test values. I know we usually go with the easiest values possible just so we can simplify calculation, but the easiest values here are going to be 0 and 1. However, I would like to use different values for a good reason, because I don't want to make a confusion with the second part of this problem, for which the values will be basically the same, and well, you'll see. So instead, I'm going to use another test value. How about -2, and I'm going to use the value of 5. I know, instead of 0 and 1, I'm using other values. So test the value, which is -2 and 5 on that side. We're going to test x equals to -2, and we are going to test x equals to 5. So what we're going to do, we test these two values in the second derivative, not in the original function. We're going to use the original function for points of inflection instead. So let's see, when we evaluate the second derivative at -2, the second derivative, which is 6x minus 3, that's a 6 times -2 minus 3, that's a -12 minus 3, which is -15. Ultimately, we need to conclude that the sign of f prime is negative. On the other hand, f evaluated at 5 equals 6 times 5 times -3, which is 30 minus 3, which equals 27. That's a positive number. All right. What is our conclusion in this case? No, it's not increasing, it's not decreasing. If the sign of the second derivative, going back to the table over here, or the definition, if the second derivative is positive, then f is concave up. Otherwise, if the second derivative is negative, then the original function f of x is concave down. So let's go back over here. So concave down, concave up. Okay, so how do we illustrate this? So in this case, it's concave down and concave up, as opposed to increasing or decreasing, which we did in the previous section. Well, concave down, I used like a sad face for concave down and a happy face for concave up. All right, well, because in this case there is a change in the concavity, well, then we have a point of inflection. So and that point of inflection for x equals whatever the hypercritical value is, which in this case is 1/2. Let's go back and evaluate the original function f at 1/2. And that's going to give us, well, the original function, which is f of x equals x cubed minus 3x minus 3/2 x squared plus 5. Okay, let's evaluate it as that function. And that's x cubed, which is 1/2 quantity cubed minus 3/2 times quantity 1/2 squared, and then plus 5. So this is going to give us a 1/8 minus 3/8 plus 5. Okay, let me fix this. Yes. And then combining these numbers, we're going to get the following 19/4. And you may use a calculator to write these numbers. All right, let's check with the graph. But actually, we have the graph of this function over here, f of x equals to negative 3x squared plus 1. So notice here we have the point 1 comma 19/4, which is the actual point of inflection here, which is where the graph changes from concave down to concave up. Right? And on the next part of the video, oh, by the way, let me express this as an order pair. That's a 1/2 comma 19/4. And this is one example on how do we use the second derivative test to find points of inflection. All right, so there's a second use of the second derivative test. And in this case, let's make a summary of what we have done. Okay. In the previous chapter, we used the first derivative to determine the intervals where a function is increasing or decreasing, and based on that information, based on finding the critical values, the test values, we determine whether we have relative maximum and or relative minimums, or both at the same time. And that is, we did this by means of using the critical values. Now, on this section, we are using the second derivative to determine the intervals where a function is concave up or concave down, and the points of inflection, if any, if there's changes in the concavity. And we did this not by using the critical point, by using the hypercritical points. And these critical, not points, rather values, came from the derivative set equal to 0, and the hypercritical values come from setting the second derivative equal to 0. That's the difference. All right, so this third point, and that's going to be something new. For the second derivative can also be used to determine whether a function has a relative maximum or a relative minimum. Oh, but wait a minute. Isn't it the second derivative for concavity? And isn't it the first derivative for max and mins? Well, that is true. However, we are going to put these two together. So we, in a way, do the maximum and minimum in it's not necessarily a shortcut, but in a shorter way rather than testing every single value using the first derivative. And well, how are we going to do this? Well, we're going to use the second derivative to determine whether a function has a relative maximum or a relative minimum point. And this is done by evaluating the critical values, that is, from the first derivative. Recall that critical values, and I'm color coding this with green to represent critical values from the first derivative, but in this case in the second derivative. And then let's see the definition. Second derivative test for local extrema. So f is a function, and f prime and f double prime both exist on the interval a and b, and c is a critical value in the interval ab. And well, the fact that f prime of c equals 0, that means it's a critical point, or critical value rather. So those critical values from the first derivative, we will plug them in the second derivative. Okay, so if the second derivative evaluated at the critical value is positive, we're gonna have a minimum. Otherwise, if the second derivative evaluated at the critical point evaluated at the second derivative is a negative value, then we are going to have a maximum. These are reversed, and I will explain why in a second. So in this case, well, on the third case, if the second derivative gives a 0, well, then the test is inconclusive. Let's go back to the graph over here. Notice here how we have a maximum value, and here we have a minimum value. Now, around the maximum value, what is the behavior of the graph? Isn't there concave down? That is, the second derivative is negative. You know, f double prime is less than 0. That's a negative. That, for this reason, we have a relative max. But on the other hand, where the graph is concave up, that's where we have this minimum point. So f double prime being a positive value means that it's greater than 0, means rel min. All right, so let's see. Let's use the second derivative test to determine the relative extrema for the function in example 3. And well, for that original function, we have f of x equals x cubed minus 3/2 of x squared plus 5. We found the first derivative to be f prime, the first derivative, which is 3x squared minus 3x. And the second derivative of the function is 6x minus 3. Now, what we're going to do is set the first derivative equal to 0, that is 3x squared minus 3x, and to find the critical values. We're not going to use the hypercritical values, but the critical values, that is, factor out this polynomial, 3x times x minus 3, set it equal to 0. From here we get 3x equals to 0, and x minus 3 equals to 0, for which x equals to 0 and x equals to 3 as the critical values. So this is what we are going to do. We will plug in the critical values, that is, the values that make the derivative equal to 0. In this case, x equals to 0 on the second derivative. That is f double prime evaluated at 0. That's a 6 times 0 minus 3, which is 0 minus 3, which is equal to negative 3, which is a negative number, that is less than 0. On the other hand, at x equals to 3, f double prime evaluated at 3 equals 6 times 3 minus 3 equals to 18 minus 3, which is 15, which is a positive value in this case. What does that mean? Well, it means that at the points where x equals to 0 and x equals to 3, we have a negative concavity, that is concave down, and at the point where x equals to 3, we have a positive concavity, that is concave up. But ultimately, this means that we have a relative max and relative min. That's what it means in this case. So now we need to find the order pairs for those relative maximums and relative minimums. So we will evaluate f at 0, which is 0 cubed minus 3/2, 0 squared plus 5, and this will be the point 0, 5. So that is our relative max. The point 0, comma 5. And on the other hand, f, oh not prime, just f evaluated at 3, this will be 3 cubed minus 3 halves times 3 squared plus 5. Oh, this one will require a few more calculations. Well, I have to do this by hand. I don't have a calculator on me. That's 27 minus 27 halves plus 5. Okay, plus 5. So let's do this over 1 and multiply, divide by 1. So that's 27 times 4, times 2. That's 54. 54 minus 27, that's going to be 27. So that's a 54 halves minus 27 halves. Or let me do this 5 over 1 as well. So we can have all halves. 2 times 2, that's going to be 10 halves. So 54 minus 27 is 27. 27 plus 10, that's 37 over 2. So we have a real mean at the point 3, comma 37 over 2. All right, let's go back and confirm that. So indeed, for this function, we're going to have a real max 0, comma 5. And over here, we're going to have a relative min at the point 1, or not 1, it was actually 3. Actually, I just realized I made a whole mistake here. Okay, I'm gonna take this, okay, so I will have to fix this whole thing, because when I factor this, if this one was supposed to be a 1, so please go back and change all this. That has to be also a 1, and that's a 1, and that's a, anyway, we are going to get the same conclusions. So that's at 6 minus 3, which equals 3, positive, and 1. And so we need to change this to this calculation. Let me erase this whole thing. Everything else was fine. Because I was looking at the number and suddenly I thought it was really, really big. Okay, so 1, and in this case, so 1 cubed minus 3 halves of 1 squared plus 5. So we're going to have 1 minus 3 halves plus 5. I'm going to write this as over 1s and have LCDs. So that's going to be 2 minus 3, which is -1, -1 plus 10. -1 plus 10, that's going to be positive 9. That's going to give us 9 halves. Right, let me go back to this point over here. 3, comma 9 halves. So yes, it was already too big. That 30, 37, or 34 over 2 was really, really big. So that's how we use the second derivative test, but to find local extrema. And well, I wanted to make this video a lot shorter than the other ones. Of course, depending on what you have for the equation, when you set up the second derivative equal to 0, you may need rational equations or even radical equations. The idea is that this problem is very similar to what we did in the previous section. I suggest to do the box so you can write down what the interval and the test values are. And sometimes even if there's changes in the concavity, but around that change there is like an asymptote, well, the concavity change is fine, but there's no inflection point because really there is no point because of the asymptote. So depending on the situation, depending on the function. And well, so this is the end of this video. I'll see you in the next one.